Welcome to the deep dive. Today we're digging into something really fascinating, automated scientific and algorithmic discovery.
Yeah, it's a pretty exciting area. We're looking at a research paper about a system called AlphaEvolve.
Right, AlphaEvolve. And it's described as a coding agent that's, well, it's not just solving problems, is it? It's sort of learning how to solve them.
Exactly. That's the core idea. Instead of, searching directly for a solution, AlphaEvolve evolves the actual algorithms, the code itself, that finds the solutions.
Okay, so it's like building a better shovel instead of just digging harder.
Something like that, yeah. It's developing the discovery tool itself. And this applies across loads of areas, finding brand new algorithms, or even just making existing computer processes way more efficient.
And this isn't just theoretical, right? You mentioned this paper details actual breakthroughs.
Oh, absolutely. This isn't just AI hype. AlphaEvolve has already cracked some pretty tough nuts, getting results better than the previous state-of-the-art in mathematics, computer science, and even optimizing parts of Google's own huge infrastructure. So, yeah, real-world impact.
Okay, so that's definitely something worth unpacking. Our mission, then, for this deep dive is to really get a handle on the key ideas behind AlphaEvolve, look at some of those big achievements you mentioned, and think about what this kind of tech might mean, down the road for discovery in general.
Sounds like a plan.
Okay.
So, where should we start? How it actually works?
Yeah, let's get into the nuts and bolts. How does AlphaEvolve function? You mentioned evolution.
Right. So, at its heart, it's an evolutionary algorithm.
Yeah.
Basically, it develops programs bit by bit, improving them based on how well they perform on some defined scoring system, some evaluation metrics.
Okay, so if I wanted to use this, what would I need to feed into the system?
Good question. First, you give it the problem definition. What are you trying to solve?
Makes sense.
Then you provide an initial program. And it doesn't have to be great. It can be quite basic, just a starting point. And you mark out specific bits of that code using special comments like #evolve_block_start and #evolve_block_end.
So you're telling it, okay, AI, focus your evolution efforts here?
Precisely. You're guiding its creativity. And the next really crucial bit is an automated way to evaluate solutions.
The scoring system you mentioned?
Exactly. Typically, it's a function, often called evaluate, that takes a program, a potential solution, and spits out some numbers, some scores, that AlphaEvolve tries to maximize.
And this evaluate function could be simple or complex?
Yeah, it could be super simple, like checking if a math property holds true. Or it could be really involved, like running a whole search algorithm or even training a machine learning model and seeing how well that performs.
Wow, okay. So a lot of flexibility there.
Definitely. And then you can optionally add some specific configurations just to fine-tune how the evolution happens.
Okay, so problem, starting code with marked sections, and the automatic judge the evaluate function. What happens next? What's this evolutionary cycle look like?
Right, the loop. It kicks off with prompt sampling. AlphaEvolve looks into its memory, a database of programs it's found before that showed some promise.
Okay.
It uses these examples plus instructions about the current problem to build these really detailed prompts for large language models, LLMs.
Rich prompts, the paper calls them.
Yeah, very rich. They can include specific context, equations, maybe even snippets from research papers, and something called stochastic formatting.
Stochastic formatting, what's that about?
It's basically about slightly varying how the prompt information is presented each time, shaking things up a bit.
To stop the LLM just getting stuck in a rut, encourage creativity.
Exactly. Keep it generating diverse, novel ideas. And what's really neat is that AlphaEvolve can even evolve the prompts themselves. The LLM can suggest ways to improve the questions it's being asked.
Okay, that's meta, a self-improving prompt system. So the LLMs get these detailed prompts. Then what?
Then comes the creative generation stage. AlphaEvolve uses a mix of powerful LLMs. The paper mentions an ensemble of Gemini 2.0 Flash and Pro to balance speed and quality. Flash is quick for rapid ideas. Pro is maybe a bit slower, but better for deeper reasoning.
Gotcha.
So these LLMs digest the prompt and suggest changes to the code. Often these are diffs, specific changes in a search replace format.
Targeted edits.
Right. Or if the code block is really short, it might just suggest rewriting the whole thing.
Okay, new code variations generated. Now we need to see if they're any good, presumably using that evaluate function again.
You got it. That's the evaluation step. The new programs get scored automatically. And to be efficient, it often uses an evaluation cascade.
Cascade, like levels of difficulty.
Kind of. Test on easy cases first. Only if it passes those does it move on to the harder, more time-consuming evaluations. Saves a lot of compute power.
Smart. And this evaluation can run on many machines at once.
Oh yeah, it's highly parallelized. Plus, it can even incorporate feedback from the LLMs on things that are hard to put a number on, like code simplicity or elegance.
Interesting. So not just raw performance scores.
Right. And it can optimize for multiple scores simultaneously, which sometimes, counterintuitively, helps improve even a single main target score.
Okay, generated, tested, now the survival of the fittest part. The evolution.
That's the evolution phase. The promising programs, the ones that scored well, along with their scores, get saved into the sophisticated evolutionary database. It uses strategies inspired by things called MAP elites and island-based models. Think of it like having different teams or islands exploring different types of solutions.
Right.
While MAP elites make sure you keep not just the best solutions, but a diverse range of good solutions. It balances exploring new avenues with exploiting promising ones.
Balancing exploration and exploitation, a classic challenge.
Exactly. And the whole thing is set up as a distributed pipeline. All these steps, prompting, generating, evaluating, are happening asynchronously all at the same time, just churning through possibilities.
Maximizing throughput. Okay, that paints a really clear picture. Now, the paper makes a point of comparing AlphaEvolve to its predecessor, FunSearch. What are the really big steps forward here?
Yeah, there are some major differences. First off, scale. AlphaEvolve can evolve whole code files, hundreds of lines potentially. FunSearch was pretty much stuck with single, short functions, like 10, 20 lines.
That's a massive difference in complexity.
Huge. And then there's evaluation time. AlphaEvolve can handle evaluations that take hours, running in parallel on things like TPUs or GPUs. FunSearch needed really fast evaluations, like under 20 minutes on a single standard CPU.
Okay, so it opens the door to much harder problems where just checking a solution takes significant time.
Absolutely. Also, AlphaEvolve gets more bang for its buck from the LLMs. It uses far fewer samples, thousands versus millions for FunSearch.
More efficient use of the AI.
And it actually benefits from the really big state-of-the-art LLMs, whereas FunSearch apparently didn't get much advantage from larger models beyond a certain point. Plus, the prompts AlphaEvolve uses are way richer, packed with context and feedback, unlike FunSearch's more minimal prompts. And finally, AlphaEvolve can juggle optimizing multiple metrics at once, where FunSearch focused on just one.
So bigger code, longer evaluations, better use of top LLMs, richer context, multiple goals. Sounds like a pretty fundamental upgrade across the board.
It really is. But there's still a limitation, right? The paper mentions one.
Yes. The need for that automated evaluation metric.
Exactly. If your problem requires, say, human taste or manual lab experiments to judge success, AlphaEvolve isn't the right tool. It shines in math, computer science, system optimization areas where you can define success clearly and measure it automatically.
Makes total sense. Okay, let's get to the really exciting part, the achievements. What has this thing actually done? The paper mentions some big wins in mathematics.
Oh yeah, the math results are pretty stunning. It was tested on over 50 open mathematical problems.
Open problems, like unsolved challenges.
Yep. And on about 3/4 of them, it matched the best solutions humans had found, which are often thought to be optimal anyway.
Okay, so it's keeping up with the best mathematicians.
But here's the kicker. On about 20% of those problems, it actually beat the state of the art. It found new, provably better constructions.
Wow. It actually surpassed human discovery on established open problems. Can you give some examples?
Sure. One is Edu's minimum overlap problem. AlphaEvolve improved the known upper bound. Another is the kissing numbers problem, how many spheres can touch a central sphere without overlapping. In 11 dimensions, it improved the known lower bound from 592 to 593.
Finding one extra sphere arrangement in 11 dimensions, that sounds incredibly hard.
It involves finding the precise coordinates for 593 points, satisfying specific distance rules.
Yep.
Definitely non-trivial. It also improved bounds for things called autocorrelation inequalities and refined a construction for an uncertainty principle in Fourier analysis.
Oh, okay. A range of deep mathematical topics.
And there's a whole bunch of results in packing problems.
Like fitting shapes efficiently. Tetris on steroids?
Sort of. It found better ways to pack hexagons inside a larger hexagon for both 11 and 12 inner hexagons. Better ways to arrange points in 2D and 3D, to minimize the ratio between the largest and smallest distance between any pair.
Okay.
It improved results for the Heilbronn problem, placing points in a shape to maximize the area of the smallest triangle you can form. It did this for points in a triangle and also in convex shapes.
Right.
And even packing circles inside squares or rectangles to maximize the sum of their radii. It found slightly better packings for several specific numbers of circles.
It's amazing how many seemingly simple geometric questions are actually really hard open problems, and AlphaEvolve is pushing the boundaries there.
Exactly. It's not just matching human efforts, it's actively finding better solutions in quite a few cases. The implications for math research are, well, pretty significant.
Absolutely. Now, what about computer science? The paper mentioned that too.
Yes, and some equally big headlines there. One major one: faster matrix multiplication.
Oh, that's fundamental to almost everything computational, isn't it?
Totally. AlphaEvolve improved the state-of-the-art for 14 different specific sizes and types of matrix multiplication.
14 improvements. That's impressive.
But the standout result was finding the first ever algorithm to multiply two 4x4 complex-valued matrices using only 48 multiplications.
Whoa. What was the previous best?
49. Using Strassen's algorithm, which had stood for 56 years.
It broke a 56-year-old record in fundamental computation. That's incredible. How did it even find that?
The paper mentions the evolution involved big changes to the initial program. Things like the optimizer used, how weights were initialized, the loss function, even the hyperparameters. It wasn't just a small tweak.
Deep algorithmic discovery. Okay, besides matrix multiplication, what else in CS? You mentioned Google's infrastructure.
Right. Real-world optimization at massive scale. It was used for data center scheduling within Borg, Google's cluster manager.
Borg, right. Managing all the servers.
AlphaEvolve discovered a surprisingly simple heuristic, a rule of thumb, for scheduling jobs better. And this simple rule recovers, on average, about 0.7% of Google's entire fleet-wide compute resources.
0.7% might sound small, but across Google's scale, that must be an enormous amount of computing power saved.
Absolutely massive. And interestingly, they chose AlphaEvolve over, say, deep reinforcement learning, partly because the resulting heuristic was easier to understand and debug. Interpretability was key.
That makes sense for such a critical system. You need to trust it.
Definitely. It also helped with enhancing Gemini kernel engineering. It optimized tiling heuristics, basically, how data is chopped up and fed to the processors for a key part of the Palace library used in training Gemini models on TPUs.
Making Google's own AI training more efficient.
Yep. And even assisting in hardware circuit design. It optimized a Verilog implementation, that's a hardware description language, for an important arithmetic circuit in TPUs.
It's optimizing the actual chip designs.
It found a way to remove some unnecessary bits, reducing the circuit's physical area and power consumption while keeping it correct.
Down to the silicon level. That's amazing. Anything else?
One more pupil. Directly optimizing compiler-generated code. It took the low-level code produced by the XLA compiler for the flash attention kernel.
Flash attention, key for transformers like ChatGPT and Gemini.
Exactly. And AlphaEvolve optimized that compiler output, achieving a 32% speedup in the kernel itself and 15% in related processing, while rigorously checking that the math stayed correct, of course.
Taking highly optimized compiler code and squeezing out another 30%. That's remarkable. It really shows there are efficiencies hiding even in places we thought were already pushed to the limit.
It really does. And the paper digs into why it works so well. They did ablation studies turning off different parts to see the impact.
And what did they find? What are the crucial ingredients?
Two things really stood out. Using that rich context in the prompts we talked about, and using that powerful ensemble of different LLMs, both made a big difference to the results.
So it's that combination again. The evolutionary search guided by the sophisticated understanding and generation power of modern LLMs.
Seems to be the magic formula, yeah.
And how does this fit into the broader picture of AI research? The paper mentioned prior work.
Well, it clearly builds on decades of work in evolutionary computation, genetic programming. That's the foundation.
Right.
It also connects to newer efforts using LLMs for scientific discovery in various fields. But AlphaEvolve seems to stand out because of its scale, its flexibility across different problem types, and its generality.
And maybe the way it uses code and metrics.
Exactly. Relying on programs as the hypotheses and having those automated evaluation metrics really helps guard against LLM hallucinations or making stuff up, which can be an issue with purely language-based AI discovery tools.
Gotcha. It keeps it grounded in something verifiable.
Precisely. The paper even hints at potentially combining AlphaEvolve's approach with more natural language systems in the future, like something called AI co-scientist.
Interesting. So bringing together different AI strengths. Okay, this has been a fantastic deep dive. Wrapping things up, what are the main takeaways here?
I think the big one is just how powerful this combination of evolutionary algorithms and large language models can be for automating discovery, both scientific and algorithmic.
Yeah, it's clearly not just theory anymore.
Not at all. It's achieved real significant breakthroughs, from fundamental math problems that were stuck for decades to optimizing incredibly complex real-world engineering systems at Google. And that reliance on automated evaluation gives it a rigor that's really compelling.
It avoids some pitfalls of just having an AI chat about science.
Right. Okay, so maybe a final thought to leave our listeners with.
Yeah, let's do that. Here's something to chew on. AlphaEvolve has shown it can optimize things we already thought were highly refined, like TPU circuits or compiler code. So what does that imply?
Yeah.
What completely new efficiencies, or maybe even entirely new scientific ideas, could emerge as this kind of technology gets better and gets applied even more widely?
Could we be looking at a whole new way of doing science and engineering?
Maybe. Could this be the start of a new era of AI-driven breakthroughs that really change our understanding of the world, our technology, the fact that it even improved its own infrastructure, that hints at a kind of self-accelerating cycle of discovery and optimization, doesn't it?
It does indeed. A potentially very powerful feedback loop. Definitely food for thought.
Absolutely. Well, thanks for joining us for this deep dive into AlphaEvolve.